So if we're talking about our activation energy and our temperature dependence of our rate constants, first we want to remind ourselves of collision theory, which we've covered in Chapter 5 for our gases, and it was also covered in that TED Ed video that I had you watch at the beginning of this chapter. So what collision theory essentially deals with is that for a reaction to occur, our molecules have to collide with the correct orientation and they have to have sufficient energy. So what that gets us in terms of our rate is our rate then is going to be proportional to our number of collisions over time. And more collisions mean that you have a better chance of being in the correct orientation and having sufficient energy. This concept of having this sufficient energy and correct orientation goes into our concept of the activation energy. So if we look at graphically, we have time and then we have energy. Previously, we've seen a graph similar to this where we start with our reactants, we end with our products, and we have some sort of pathway that we have to take in between. Now we know that this energy that has to be overcome in order for our reaction to occur, that's what this is referring to. That's what our collision theory is contributing to, is that we have this certain criteria that have to be made for our reaction to actually go. Okay. And this here is our activation energy, or energy of activation, so EA subscript, or sometimes it's E act. That is our activation energy. We introduced this concept of this graph here way back in Chapter 6 because we talked about the difference between energy of our reactants and our products. That was our enthalpy, right? And in this case, this delta H would be negative because we're losing energy. So this would be an exothermic reaction. We can also look at a similar description here. I'm going to kind of run into my words there just so I have another space to put a third graph here. But we have time, energy. We can put our reactants lower than our products. We still have an energy of activation that we have to overcome. But still the difference in our products and our reactants, that's our delta H value. This would be positive, so this is an endothermic reaction. For kinetics, we're starting to care about the pathway that we're taking. Okay, so originally we just ignored this. We knew it existed, but we just looked at our starting and our final. Okay, our starting and our final position. But with kinetics, we want to start now looking at this whole pathway. Okay, what exactly is going on to create this shape? How much is our energy of activation, and why do we have to put in that certain amount of energy? So what happens is this top portion where our activation energy, that's where our peak occurs. This is called an activation complex. We can also call them transition states, so aka also known as And in terms of looking at a reaction that could happen, say, in 2 steps, if we have a reaction mechanism, we can also look at a graph very similarly. And we have time, energy, we have our reactants, we have our products. Instead of just having one hill to get over, we could have two. And they may not be the same energy. Actually, let's make one kind of higher. So we're going to ignore that. Ignore this one. So now what happens is we have this larger hill that we have to get over. And then we have a smaller hill and get to our products. Because this hill here is larger, this first portion, this would be our rate determining step. We'd still have an activation complex here, okay, or a transition state. This bottom lull, that would be our intermediate. Energy of activation is that largest amount of energy that we have to put in. And our concept of our enthalpy change still remains the same in that it's just the difference in our reactants and our products. So definitions for us, make sure we have our activation energy. So our activation energy is what we need, the energy that we need for a reaction to take place. Okay? And even an exothermic reaction, one that gives off heat, does require a certain amount of energy to actually get the reaction going. So one way that we can, say, speed up our reaction, get our reaction to go towards our products, is to increase our kinetic energy of our molecules so that they're moving faster, they're having more collisions, so that hopefully our rate then will increase. Okay, so typically how we increase our kinetic energy of our molecules is by raising the temperature. One thing to keep in mind, since we are talking about kinetics, raising the temperature is going to affect our rate constant, and we're going to use the Arrhenius equation to be able to relate rate constants to two different temperatures. So if we change our temperature, our rate constant is going to change. So our Arrhenius equation is going to calculate the dependence of our rate constant on temperature. So our rate constant is going to be equal to A, which is called a frequency factor. Essentially, it's a value that puts a number on our collision frequency. And we have E to the negative EA, activation energy, per R times T. So K is our rate constant. A is our frequency factor. Basically our collision frequency. EA is our activation energy. R is our gas constant. We want it in units of energy. So you're going to want the 8.314 joules per moles Kelvin. Watch your units on energy of activation. If this is in kilojoules, you're going to have to convert R. And then T, of course, is temperature. We want that in Kelvin. Another form of Arrhenius equation puts it into a linear form. So we have natural log of our rate constant is equal to natural log of A minus EA over R, these are constants, times 1 over T, that's our variable. Okay, so you have your y equals b minus mx form. Or we can put this equation looking at two different temperatures. What is our rate constant? So we have natural log of K2 over K1 is equal to energy of activation over R times T2 minus T1 divided by T1 times T2. So this is kind of similar to the Clausius-Clapeyron equation, same kind of concept. So remember, with your experience with your book, the internet, and sapling, depending on how this temperature portion is expressed, that will depend on if it's K2 over K1 or K1 over K2. So just be aware of that. For this equation, you need to know how to use it, but the equation itself will be given to you.